Here's an example that illustrates the power of energy conservation. Consider a projectile launched with a speed v sub 0 with an initial angle theta above the horizontal, launched from height h above the ground. We're going to use energy conservation to determine the final speed, or the speed of this projectile at impact. We'll solve this symbolically. Now you might think that we'd need to know the angle above the horizontal, but we don't actually need to know this to find the final speed. We'll see in this problem that the final speed, the speed at impact, is independent of the angle theta, which is pretty amazing. Okay, so let's get started by writing down energy conservation. The change in energy of the system is equal to the work done on the system plus the thermal energy delivered to the system plus any other energy transfers. We won't write them all down here because there could be a lot of those. Now we need to consider our system. Now, one of the things we might want to use in this problem is that this projectile changes height above the ground from here to here. So we might want to use the concept of potential energy. But if we want to use the concept of gravitational potential energy, we need to consider a system that consists of the projectile and the Earth. So let's do that. Now, this choice of system, it's consisting of the projectile and the Earth. There's nothing in here in this problem that's doing any work on that system. We're not worried about thermal energy transfers to that system. Sure, there's sunlight and stuff, but we're not worried about that affecting the problem. So basically, as far, to a good approximation, the change in energy of this system is going to be zero. All these ways of transferring energy into this system are either zero or irrelevant. Okay. Now we need to think of the forms of energy that can change in this process. Of course, this is the total energy of the system. The forms we have in play are kinetic energy and gravitational potential energy. Now, we're not really worried about changes in the Earth's kinetic energy, but we do have change in the projectile's kinetic energy, and we certainly have a change in the potential energy of the projectile Earth system because of this change in height. So let's put those in. The Earth's kinetic energy isn't changing in this process appreciably. So this is the change in kinetic energy of the projectile, and here's the change in gravitational potential energy of the Earth projectile system. All right, so let's plug those in. In this expression, m is the mass of the projectile. So there's the projectile's final kinetic energy at impact. Here's its initial kinetic energy at launch, and this is the change in potential energy of the projectile Earth system. Now note this change in y, when we use this formula for gravitational potential energy change, we have to be taking y as the positive upward direction. So the change in y from this final, from initial to final, is down by minus h. So we can plug that in here. We can divide both sides by m and multiply both sides by 2, and then we get. Finally, we can solve for the impact speed. Now, so here's our result. We can see that the impact speed depends on the initial speed, depends on how high the projectile was initially above the ground. All that stuff makes sense, but note we don't see any angular dependence on here. That's very interesting. But we need to be very clear that we're talking here about speeds and not velocity. The impact velocity will certainly depend on the angle of launch. For example, if this were thrown straight up with an initial speed v sub 0, when it hits the ground, it'll be coming down, it'll be heading straight down. It'll have this final speed, same final speed, but it'll be going straight down instead of at an angle. So the final impact velocity will have an angular dependence, but the impact speed does not. Now, if we wanted to, we could actually use this as another way, as a handle to sort of make progress on getting the impact velocity. For example, v final, that's the magnitude of the impact velocity. We know that the horizontal component of the impact velocity will just be v sub 0 times the cosine of theta. So we could use the Pythagorean theorem relationship between the magnitude of a vector and its components to get the y component of the impact velocity. And then finally, if we wanted, we could compute the direction of the impact velocity from the knowledge of the components, the y component and the x component of the impact velocity, using the arctangent function. Okay, that's all.